oh, sorry. For us, yeah, for us, radius was 1, wasn't it? Okay, so radius is 1. So I'm going to write that up here. I know that the equation of this circle is this. That's great. Oh, shit. That's great. But this is a polar region. It is a polar region. I mean, it's a circle, right? The problem is it's not a rectangular polar region. I can't say my theta is stuck between two constants and my radius is stuck between two constants. Not unless it was centered, right? If that would have to be centered. That circle would have to be at the center of the xy plane there. So what I'm going to do is something you haven't seen yet, all right? How do we get this equation from the equation of a circle in Cartesian to the equation of this in polar? Well, as you might suspect, we can first expand everything out. Right? That's just me expanding x minus 1, that quantity squared, right? Do y'all recognize anything in there? X squared plus y squared, right? That's equal to what? R squared. Okay, so we have r squared. Okay, minus 2 times, well, what's x when you go to polar? R cosine theta, right? And then you have plus 1, but on this side you have plus 1 as well, right? So you can subtract 1 on both sides. And you get equals what? 0. Okay, what the hell? All right, now I want you to notice that these both have a common factor of r, right? So r can be factored. Now you have r minus 2 cosine theta equals 0. And now this means that you set each of these equal to 0. You either have r equals 0 or what? Or r minus 2 cosine theta equals 0. So either r equals 0 or r equals what? 2 cosine theta. What does this mean, right? Like, what does that mean to us? It means that if you want to draw this circle, then what you're going to need to do is you're going to need to let your radius, remember in polar you're standing at the origin and you're standing here and you're looking out and you're saying, give me an angle, right? Give me an angle and give me how far to walk out. And this is saying that to be on this circle, you either have to walk out nothing, right? Or you need to walk out how far? 2 cosine theta. All right? So let's just try some values. This is not necessary, I just want you to really understand what's going on. If theta is 0, then what's r? If theta is 0, cosine of 0 is 1, so you're 2, right? So that means when you're standing here and you're aimed out at 0 degrees, you walk out, what, 1, 2, and now you're right there, right? Okay. Now let's take another angle we know pretty well. How about pi over 4? Okay, what's cosine of pi over 4? Root 2 over 2, so this is 2 times root 2 over 2, which is just root 2, which is about 1.414. So that means that if you're standing here and you aim pi over 4, which is, what, 45 degrees? You walk out how far? So aim 45 and walk out how far? 1.4. You'll be right there. You'll be at this point right here. If you were to do like pi over 6, you'd walk out and you would be here. What about pi over 2? So 2 times, what's cosine of pi over 2? 0, so you'll be at 0. So that means when you are aiming straight up, right? When you're aiming straight up, how far do you walk out? You don't. And that means you're here. Okay? Y'all understand how this is working? As you increase the angle, it tells you to walk out a certain distance. So as my angle keeps going up, I keep walking out a certain distance. And when my angle gets straight up, it's saying stay still, don't go anywhere. Okay? Now let's keep going. Let's aim this way. What's that angle right there? What would happen if I did pi over 4? What is it? 3 pi over 4? What would happen if I do 3 pi over 4? I get 2 cosine of 3 pi over 4. It's cosine of 3 pi over 4. Negative root 2 over 2. And those cancel, you get negative root 2. So what is that telling you? When you go and you aim at 3 pi over 4, which is right here, when you aim that direction, what am I supposed to do? Walk out how far? Backwards. Negative. So I take negative 1.414 and I'm here. You see? And then what happens if we go to pi? 2 cosine of pi. Cosine of pi is negative 1, but then times 2? 2. So when you're aimed at pi, you walk where? Backwards 2. So all of these angles from here to here gave you the other side of the circle. Kind of weird, right? Now you could have also, that's not the only way, so that's not the only way to draw that circle. We could have, this what I just showed you, all we had to do was let theta be between where and where. To draw just a full circle, we needed theta to go from 0 to pi, right? That worked? 0 to pi would have drawn me the circle. Or you could have also done this. You could have let theta go from the biggest be pi over 2. Remember pi over 2 was when we were straight up and we said don't go anywhere? You could have gone from, instead of going from 0 all the way to pi, we could have stopped at pi over 2, but then we also would have wanted to go backwards. And so go not to 0, but to negative pi over 2. So if you were to plug in, let's pick a value down here. What's a value down there? Let's go negative 45 degrees. That's negative pi over 4. What would happen if you plug in negative pi over 4? So 2 times cosine of negative pi over 4. Cosine of negative pi over 4 is root 2 over 2. So this would be root 2. So if you're aimed at negative pi over 4, there, you walk out root 2, which puts you there. So I guess what I'm getting you to see here is that there's multiple ways to draw that circle. Here's the formula for it. Sorry, here's the formula to draw the circle. It's just a question of the restriction on theta. If you go from 0 to pi, you'll draw one circle. If you go from negative pi over 2 to pi over 2, you'll draw one circle. Yes?
Does that mean quadrant 3, you can't have anything there?
You would just draw the circle again.
Oh.
You would draw it on top of itself. Gotcha. Right? If I just say, hey, here's the equation, just let theta be all real numbers, just let theta go forever, you just keep drawing the circle on top of itself over and over and over and over and over. Okay. Shit. What are we doing? I forgot. What is this problem about? Oh, well, we were trying to define the region, right? The region. Well, that's different, right? We don't want the red circle. We want the stuff inside it and on the edge. So remember, we need not only the edge, but everything in between. So when I was sitting here saying, look out this way, right? And then walk out 2, we actually want everything between there, don't we? And then when we aim up at this one, we don't want that point, we want everything between it. So we want that, we want that, we want that, that, and stop, right? And when we go, let's use this one, I like this one. When we go backwards, we want that, everything between, back. So I'm trying to define this region using polar coordinates, but not rectangular, right? Not between two constants. Between theta is going to be between two constants, right? So I'm finally ready for this polar here. My theta is between two constants. Let's go negative pi over 2 to pi over 2. But my r is not between two constants. It's between what? What's the smallest r I want? 0, and then to 2 cosine theta. And do you see there that that this is some function of theta? I think I call it h2 of theta. On the notes, I call this is h1 of theta. So you've got your theta's between two constants, but your r's between two functions of theta. And then we can set things up. Right. Remember what we were trying to do? Find the volume of that? Okay, so we need now to set that double integral up. So that double integral is going to be double integral over R, which is that region we just defined here. And then we have the top surface. What was the top surface? It's the equation of the sphere, but solved for z. And remember, the sphere was x squared plus y squared plus z squared equals 9, right? Because the radius was 9. Or the radius was 3. So when we solve that, we get square root of 9 minus x squared minus y squared, right? Okay, and then dA, right? That's what we want.
Are we doubling that?
You want to do that now? I was saying getting the red, but it's up to you.
No.
We'll just do that. So this is going to be the volume of the red.
Gotcha.
Then we'll double it later. All right, so now, excuse me, I'm ready to go to my polar. Let's do it all in one shot here. I know for sure my outer integral has to be with respect to what? The outer integral. The thing that has the constant. So I have d theta out here. That'll be from negative pi over 2 to pi over 2. Okay, and now my inner one has to be dr. I also need an r there, don't I? There's that r, don't forget it. What are our limits of integration on r? 0 to 2 cosine theta. And then the thing I'm integrating, square root of 9 minus r squared. Kind of the same thing from before, right? Replacing the minus x squared minus y squared with minus r squared. Could you integrate this with respect to r? I think so. Basic u sub, right? And then you're going to replace r with 2 cosine theta and 0 and then integrate that with respect to theta. So that's the setup of the integral. Now I went ahead and did the work already. Now I did mine a little bit different, but you can see I went ahead and went from 0 to pi. Okay, I went from 0 to pi instead of negative pi over 2 to pi over 2. And I went ahead and doubled the answer. Okay, so this is the volume of, not the red piece, this is the volume of the yellow piece. And then I did 4/3 pi r cubed on the calculator, on the computer, got 36 pi. And then I took that answer and subtracted this one. Wait, what the hell did I do? Oh yeah, yeah. Okay, so I took there's the volume of the sphere, and then I added to it the negative of this. So yeah, I don't know why I typed it in that way, but so the final volume should be about 95.93 ish. Okay. Did we do this in here? Prove the area of a circle is pi r squared. Prove the area of a circle is pi r squared. Well, there's a lot of ways to do that. So let's see here. Didn't we learn this? I said it was really important. Didn't we learn that if you take the double integral over some region R of 1 dA, that that's just the area of R? Do I remember me putting that up there? I said it was really important. I'm restating it again now.
Yeah.
So we're saying this. If you take some region on the ground, R, and you want to know its area, then what you can do is imagine bringing that up to a flat surface up here. Flat, right? Where that surface is exactly the equation z equals 1. Okay, z equals 1. So it goes straight across. That's not a very good picture. But then the volume of this would numerically be equal to the area of R. Because the height is 1. If the height is 1, then the volume of this, again, numerically would be equivalent to the area. All right? So that's what I'd like to do here. If I want to know the area of a circle, right? If I want to know the area of a circle, or prove that the area of a circle is pi r squared, then what I'm going to do is I'm going to do the double integral over 1 of this region R with respect to area, but the region that I'm going to use on the ground is going to be this. It's going to be a circle of radius capital R. Please don't confuse this capital R with that one. In fact, it bothers me so much that we're using capital R as two different things. Let's change this to D and change that to D. That way we're saying, okay, if you want to know if you take the double integral over some domain D of 1 dA, that's the area of that D. And that means this picture is D here. So if I want to know the area of a circle, calling that D, right? If I want to know the area of a circle of radius capital R, then I just need to do that double integral, don't I? Okay, but what type of region is that on the ground? That's a polar region on the ground, right? That's polar. So if we go to polar, right? If we go to polar, theta's between what? 0 to pi, and then what's the r between? Careful, little r. What, 0 to what? Big R. 0 to capital R. Right? That's what my radius varies between. You're going to go all the way around. Your radius goes between 0 and capital R. And now we set up the double integral. Let's do it. Double integral. Let's go ahead and put our R here. And let's go dr d theta. It doesn't matter which order you go in, right? Because they're both constants. But this time go 0 to pi. That's my outer. And my inner is 0 to capital R. And what am I integrating? This was the R I had to have here. But what's the actual function I'm integrating? 1. That's it. We're doing it. We're not going to go to a computer for this. We're doing it. This is just R, right? Let's do the inner integral. What's the antiderivative of R with respect to R, little r? What's the antiderivative? 1/2 r squared. Okay, so what we get here is integral 0 to 2 pi. The inner integral, you said the antiderivative of that was 1/2 r squared. And we're evaluating that from r equals 0 to r equals capital R, right, or big R, d theta. Okay, what happens if you plug in capital R? You get 1/2 capital R squared. Plug in 0, you get 0. And this is just d theta. 1/2 r squared, capital R squared, is a constant, right? So take the antiderivative of that with respect to theta, and you just get 1/2 capital R squared times theta, evaluating theta from 0 to 2 pi. And when you plug in 2 pi for theta, right, what do you get? You get pi r squared. And when you plug in 0, you get 0. And that proves that the area of a circle is pi r squared. Right? Kind of interesting. I think interesting. prove the volume of a sphere of radius capital R has a formula 4/3 pi r cubed. Wait a minute. We just used that formula a second ago, right? Well, yes, we did, and we believed it was true, and we still believe it's true, but we're going to prove it now, right? I told you I proved this in my Cal 2 class today, right? Today I proved this. But what we did is we wrapped something around the x-axis, and we found a volume using method of washers and all that stuff. We're going to use a double integral to do this. So what does a sphere of radius r, capital R, what is its equation? Equals capital R squared, right? That's if we center it at the origin. What do y'all say we just cut it in half and just find the volume of the top part, right? So if we do just the top part, right? Then what's the top surface? What's that top surface? We've done this third time we've done this, I think, today. That would be that solved for z, right? So that would be square root of capital R squared minus x squared minus y squared, right? And then what about the ground? What about my domain on the ground? Okay, so like the bottom is 0, right? But I'm saying in terms of the domain, the D on the ground here. What type of region is this? Circle, so it's a polar, right? Polar. Do we know the radius of this? So this is not like the cone meets the sphere, right? This is the sphere meets the ground. So this should just be capital R. Beautiful polar region. Beautiful polar region, right? In polar, that's theta between 0 and 2 pi, and R is between 0 and capital R, right? 0 and capital R. All right, so we're going to set up the double integral now. Do y'all want to go straight to polar? Go straight to polar? Yeah. Okay, straight to polar. So we got double integral. Okay, let me put out here r dr d theta. And the r, don't forget, that has to be there because we went to polar. And now I'm going to do this function, right? The square root of capital R squared minus little r squared. Do y'all see why I'm using capital R for my radius? Because if you did the little r, you'd have two different little r's and it would look weird. Yeah. Okay, there we go. That's it right there. Oh, limits of integration, sorry. Theta's on the outside, 0 to 2 pi. And then over here, 0 to capital R. All right, now we actually do need to integrate that. We do need to integrate that. Remember, R squared, capital R squared is a constant, right? Capital R squared is a constant. So U, I'm going to make a basic U substitution because I see that the derivative of this is almost that. So I need some space here. So here's what I'm doing, just so everyone's clear. I'm trying to do this integral right here. Integral from 0 to capital R, square root capital R squared minus little r squared times r dr. I'm just working on that inner integral first. I make a U substitution. U is capital R squared minus r squared. The derivative of that is just negative 2r dr. And then depending on how you learn this, yeah, pull out a negative 1/2. That's so this integral turns into the integral from, negative 1/2 integral of, this was u, so u to the half du, and then the antiderivative of that, negative 1/2 times 2/3 u to the 3/2 plus a constant, which you wind up getting negative 1/3 u, but u was capital R squared minus little r squared to the 3/2. Okay, so this is just scratch work, all right, which hopefully you can get to. This should be your antiderivative right here. Now, come back over here. You've got integral 0 to pi. Okay, now we've got in there this answer, negative 1/3 capital R squared minus little r squared to the 3 halves. Evaluating that from little r equals 0 to little r equals capital R. After we're done with that, d theta. What happens when we replace little r with capital R? That goes away. So we get 0 when we plug in capital R. Minus, careful, when we plug in 0, it doesn't go away. Plug in 0 for little r. We're left with negative 1/3 capital R squared, but then that's 0, right? And then that to the 3 halves, right? D theta. Yeah, and then this, something squared to that power, you multiply the powers, that just becomes r cubed, right? I've got to continue over here, I think. So continuing up here, we still have this integral, 0 to pi. All right, clean this up. Minus minus is plus 1/3 r cubed. D theta, right? That's it. And that's a constant. So the antiderivative of that is just 1/3 capital R cubed times theta. Evaluated theta equals 0 to 2 pi. Right, antiderivative of that is this with a theta, and then now plug in 2 pi. When we plug in 2 pi, we get 1/3 times r cubed times 2 pi, right? When we plug in 0, we get 0. And then cleaning this up, this is 2/3 pi r cubed is the volume, right? Just bring the 2 pi out front and just write it that way.
4/3.
Remember what we just found the volume of, right? This is only the top half, right? Remember this was just the top half. So double this, multiply by 2, and you get 4/3 pi r cubed. It turns out that if you do this in Cal 2 by rotating around the x-axis, it's actually easier. I think it's easier than this. But still, it just shows you that we can use a double integral to prove things like that. Okay, so we've proven today that, that you can use a double integral to find both, prove the area formula and the volume formula for a sphere, for a circle and sphere, respectively. Okay, that's going to wrap up today. Please work your homework. What's coming up next? Triple integrals. So the thing about this, and y'all can start packing up, the thing about, remember for double integrals, we could see the surface, right? And the domain lived on the ground in two-dimensional space. For a triple integral, we can't see the function, but the domain lives in three-dimensional space. Okay? So imagine how many different domains can you possibly have. Like on a flat sheet of paper, we saw rectangle, we saw type 1, type 2, then we saw polar, then polar can have a type 1 and a type 2, right? Well, with triple integrals, your domain is a solid in three-dimensional space, right? And so how many different types of solids can you have? The easiest thing would be like a box, right? And then they can get all weird from there. So in order to do a lot of different weird shapes, we're going to need Cartesian in three-dimensional space, and then we're going to need two other systems for representing points in three-dimensional space. So just like we just had for flat sheet of paper, we had Cartesian and polar. For three-dimensional, we're going to have Cartesian, cylindrical coordinates, and spherical coordinates. And those are the three coordinate systems that we're going to have to kind of become somewhat comfortable with. All right? So that's where we're headed. Y'all have a good rest of your day. Get that mini exam done if you're turning it in on, what, Wednesday? It's due?
Sir, can I ask a quick question?
Yeah, can I turn off my camera?
Oh, yeah.
Yep. All right.